Well, Mr. Sams, now that we've learned about where light comes from and kind of how it relates to the atom, there's just like a bunch of math that we have to learn.
Woohoo, math!
I love math. Math is like the language of science.
It is. It's great.
So yeah, you got to learn it. So hey, they're called the light equations. All right, let's just talk about some equations. It's going to be a lot of math. Get your calculators out, and you'll watch me use the calculator. Here are the key equations, and there's a bunch of weird symbols here. E stands for energy. And this funny-looking V, I know, I wish they'd called it an F, but that's frequency.
It's actually a Greek letter nu.
Yeah, it's actually the Greek letter nu. It looks like a funny-looking V. H is called Planck's constant. This was this Planck's equation, Max Planck. Planck's constant. I'll tell you what that is in a minute. And then C is the speed of light. And another Greek symbol is lambda, which is the wavelength.
Yep. Now, a couple things before we move on. Frequency has to be in
a unit of something of seconds to the minus
seconds to the minus 1, or 1 over a second.
1 over seconds.
It's also called hertz if you're interested. Wavelength has to be in meters.
If you have it in any other unit, nanometers is particularly common, or whatever,
Have to turn it into
kilometers, you
meters
must
first.
convert it into meter. And Planck's constant, and then energy will be in joules. All right, so those are the units.
And we'll give you H here, H and C. Oh, here's H.
Here's
right
H. H is 6.626 times 10 to the minus 34th joule seconds.
Okay,
And
so write that down,
C,
put it somewhere handy.
Just for fun, I don't think C is in the podcast.
Okay.
C is 3.0 times 10 to the 8th meters per second. That is the speed of light. It travels that fast, which is really fast.
All right, so these are just things you need to write down and know.
Yes, and then we're going to use them. Okay, so with the light equations, here's the light equations. We can also sort of resolve. If you kind of, the H's are here and here, and they will cancel. And so you can say that nu is equal to C over lambda. Or you can also take, if you cross multiply, V times lambda is equal to C. So there's lots of ways to do this because you're going to be asked to solve for each of them a little bit differently.
And for some reason,
We have
things are
weird
dancing.
animations. Okay, so here is kind of the key. I want us to fill in this particular table. So if you know the number of joules, what's the wavelength, what's the frequency, and then also what's the color? Okay, folks, so if I have 3.5 times 10 to the minus 19th joules, by the way, a lot of confusion, that's a very small number. That's actually the energy as an electron would fall from one level to another. So it's just the energy in the wavelength of one electron, of the light that is produced when you have that one electron. So if I've got E equal to 3.5, 5 times 10 to the minus 19th, I have some equations. So E is equal to HC over lambda. But you see, I know H and I know C because those are constants. So if I want to find the wavelength, I can cross multiply. So I can say E lambda is equal to HC, right? Cross multiplication here. Or I can, if I want to find lambda, I can say lambda is equal to HC over E. So H is 6.626 times 10 to the minus 34th joules seconds times 3.0 times 10 to the 8th meters per second over E, which is 3.5 times 10 to the minus 19th joules.
Joules, good.
Now let's
look.
Go ahead.
Can we cancel the units real quick and see what units are going to be left
the
with?
joules will cancel, looks to me like, and you see the seconds, one's on top and one bottom, we're going to end up with meters.
Meters, and that's what your wavelength, you need to have them in.
All right, let's pull up our calculator. So here's my calculator, so I'm going to type in 6.626. Remember, I have to do second function E when we're dealing with this, right?
That means times 10
times
to the...
10 to the power, and I'm going to say to the power of negative 34. So I've just done this number here, and I'm going to times it by the speed of light, which is 3.0 times 10 to the 8th. So 3, I don't have to say the 0, second E8, divided by this number here, the joule number, which is 3.5 E negative 19. 14. Enter. So the answer is 5.68 times 10 to the minus 7th meters. That's what? That's the wavelength. Now, I'm not just trying to find the wavelength, I'm also trying to find the frequency, which is the V, if you will. All right, so to find the V, all right, what's that equation? Okay, what equation am I going to use?
It's nu lambda equals C.
Nu.
C equals lambda nu.
Yeah, so C is equal to lambda times this funny V. So if I want to solve for V, V would be equal to
C divided by lambda.
C divided by lambda. So if I do C divided by lambda, that's going to be 3 times 10 to the 8th meters per second divided by the wavelength, which we determined just a minute ago, 5.68 times 10 to the minus 7th meters. Now, again, let's think about this unit-wise. The meters are going to cancel, aren't they?
Yep.
And you're going to end up with some number over seconds. It's going to be weird. It's technically, we call it seconds to the minus 1. So now I have my calculator up here again. I'm going to take 3e8 divided by 5.68 e negative 7th. And I get an answer of 5.3 times 10 to the 14th over seconds. Or we'd say seconds to the minus 1 is technically how you would write that.
Hertz.
Or you could say hertz. Now, there's a sort of a second question. So let's write these numbers back in our chart. So here I've just placed these into my table. And here they are right here. But then there's this sort of weird question. What's the color of this light? And I wrote color in quotation marks. So let's think about that. All right. So here is a table of the different things. And we've got the nanometers, centimeters. Well, we had it in meters.
Yeah.
And it was 5.68.
It's a really tiny meter.
It was 5.68 times 10 to the minus 7th meters. Now we've got it looks like we need, what are we going to do, Mr.
Let's
Sams?
make it into nanometers, because if we're talking actual color, it's always going to be in nanometers.
So if it's color, 5.68 times 10 to the minus 7th meters, we want to convert that to nanometers. Now using a conversion table, you can grab one somewhere. You can say that 1 meter is equal to 1 times 10 to the 9th, or 1 billion nanometers. The meters cancel, and you just move the place over 9 places, and you get 568 nanometers.
All right.
Now,
let's go back to that
let's
chart.
go back to this chart. Now, if we go back to the chart, 500 nanometers to 600, so it was 568. So here's about 550, 560. It's right in
greenish,
here.
Greenish,
I'm
yellowish.
going to call it green-yellow. So the color here is green/yellow. Now, if we were to get a number that was, let's say instead of like so many nanometers, we got 1 meter, well, then you would just quickly say, well, it's an FM radio wave. Or if you got, so you may need to convert to nanometers, but this is in centimeters. You're going to have to sort of figure that out, what color it is. Now, the reason I put the quotations around color is because the color varies based on, if it's like infrared, it's not really a color, it's just infrared. Well, let's do one more example, Mr. Sams.
Right.
Let's just do this last one. I think they got to get that. You've got to rearrange these equations, folks.
Just plug and chug.
Plug and chug. So that's what we're going to do. So we've got a frequency of 1.5 times 10 to the minus 13th. So we have a frequency of 1.5 times 10 to the 13th, positive 13th.
So we also need to find energy and wavelength.
So E is equal to H nu. Oh, well, this is going to be the easy one, Mr. Sams. So we get this is 6.626. times 10 to the minus 34th joules seconds times 1.5 times 10 to the 13th seconds to the minus 1.
Because hertz and seconds to the minus 1, same thing.
Yeah, so let's get the calculator out. So we'll take 6.626. Let me show you something, guys. It's E negative 34. Watch what I do. I'm going to push the stow button. And I'm going to say alpha, I'm going to choose H, and I'm going to push enter. Now every time I do alpha H, that number comes up.
Ooh.
And it's like saved. It's way super cool. So now all I could do is alpha H, I said pi.
You're getting a second, not alpha.
Oh yeah, alpha H. And then I can say times 1.5 E13. So I'm just using my calculator to save myself some work. And so that equals, what is it, 9.9 times 10 to the minus 21st. And now notice the units, the seconds going to cancel, and that's joules. That's a 21, not a 4. Okay, now we got to find one more thing.
We got to
Mr.
find frequency, or wavelength, sorry. So let's do C equals lambda nu.
C equals lambda nu. So what do I do here? I want to find lambda. So lambda is C over nu.
Yep.
So C divided by nu would be 3.0 times 10 to the 8th.
That's what C is all the time.
Meters per second. It's always that number divided by our frequency, which we had up here, 1.5 times 10 to the 13th seconds to the minus 1. The seconds are going to cancel, and you're going to end up with meters. So I'm going to do the calculator again. 3.0 E8 divided by 1.5 E13. Bingo, bingo, I get this to be 2.5, or 2, not 2.5, 2 times 10 to the negative 5th meters.
Okay.
That's not too bad, is it?
No.
Now, let's go ahead and fill in our chart. So here we have 2.0 times 10 minus 5 meters, and then our joules, and now we just need to find the color. So we have to look at the chart. Now, when we look at the chart, it's just best to kind of focus your eyes on the wavelength.
Yeah.
So the wavelength is kind of the key there. So if I say 2 times 10 to the minus 5, all right, 2 times 10 to the minus 5 meters. You know, if we multiply that by 1 billion, it's not going to help us out much.
Not for the actual color, no.
Yeah, but it kind of will, because it's going to give us something else. So let's go ahead and convert it to a...
Okay, to nanometers.
Yeah, to nanometers. So if I take, I need a blank screen, 2.0 times 10 to the minus 5 meters, I apply this same thing, 1 times 10 to the 9th nanometers in 1 meter. What do you get?
20,000? No, yes.
So that gives us 20,000 nanometers. So if we go back to this chart, 20,000, here's 1,000 nanometers.
Okay, so we're 20 times more than that. So we're down, looks like, infrared range?
Yeah, it's going to be right in here. You know, a lot of the charts, guys, don't give you all these in nanometers except for these down here.
Right. A lot of them give it just in meters. And so you just look up the power of 10 in meters.
Yeah. So,
and,
I'll see if I can add that as a call out right here. And maybe that will help you do that. So, yeah. So there's other ways that these charts are done. So in fact, here's that chart we were just talking about, folks. Here down the bottom here is with the wavelength. So if you find 2 times 10 to the minus 5, here's the minus 6, here's the minus 4th, and so right here we would be in the infrared. So in that box, you'll say that this is an IR light. So if you get to 10 to the second, you'd call it a long radio wave. If it's 10 to the minus 16th, actually these are the wavelengths down here, you'd get gamma rays. This is the frequency. You could look at the frequency too. These charts, it doesn't really matter. They're the same thing. They're kind of related. So folks, that's it for this podcast. Hopefully that makes sense and you understand the math of the light equations.
You guys, you really just need the 3 equations and plug in the things you know to find the thing you don't.
And you note H and you know C. These are constants.
Yep.
All right, we'll see you.
Bye.
Bye-bye.